Where are you? Are you in Illinois?
I'm in Minnesota.
You should start by introducing yourself.
My name is Thomas Dolan. I'm an adjunct professor at the University of Illinois in Champaign-Urbana, and my career has been mostly in nuclear fusion research, although I'm branching out now into molten salt fission reactors.
You've had a very long career, both in the university and at Idaho National Labs. You also worked for the IAEA. You worked at Missouri. So can you think back to what initially sparked your interest in fusion energy?
I was a senior at the University of Illinois measuring nuclear instruments and subcritical assembly. Professor Marvin Wyman told me about nuclear fusion research, which he said is a thing of the future with unlimited clean energy supply. But it's very difficult because it requires confinement of 100 million degrees. That just sounded fascinating, so I thought that'd be something I should look into after I finished my time in the Navy. So I did my 2 years in the Navy and then came back to graduate school wanting to study nuclear fusion research.
How would you advise someone to find opportunities to get into nuclear fusion?
They should learn about it and communicate with people who are doing the research at universities and national laboratories. I'll start channels of communication because they'll learn a lot more that way than just sitting at home and reading.
For most of your career, you have been a teacher.
Yes.
Do you have any advice on how to teach fusion, nuclear engineering, and fission?
At the University of Missouri, I taught some courses on nuclear fusion theory and made a textbook out of it.
That's a state school, correct?
Missouri University of Science and Technology, MUST. That's what I did. It's very good to have the students involved in doing projects where they design something for a fusion system.
After you left there, you went to Idaho National Labs. Why did you make the move?
Well, I was a consultant to Phillips Petroleum Company, and they were partners with General Atomics in an experiment called the Omakita toroidal experiment. And then that got started but lost the funding, and then EG&G became partners with Phillips Petroleum to build an experiment and continued it at Idaho National Laboratory with planning for the next device. Phillips Petroleum Company had a vice president of research, Charles Cook, who had a long-term view of technology. So he sponsored projects with nuclear fusion, solar energy, biotechnology, superconductivity, things like that that would not have an immediate payoff. Under his leadership, Phillips had the most patents per year of any petroleum industry, although they were 7th largest. So that was a great involvement of industry in nuclear fusion research and other long-term technologies. Unfortunately, in 1984, T. Boone Pickens tried to take over Phillips financially. He went $4 billion fighting the takeover attempt, and then they had to cut down the research, so they cut out all this long-term stuff. Research center went from 1,300 people down to 700 people. So that was a sad day for fusion research and industry. The attitude was that a wildcat oil well cost about $10 million, and only 1/10 of those succeed. And that was the way they did fusion research. The Omakita toroidal experiment was successful. They were going to build a $100 million experiment, but this financial takeover canceled the plans.
I'd never heard of the Omakita toroidal experiment.
And a reverse field pinch with a helical field like a stellarator. And it was successful at General Atomics and it was shut down, and later it was given to Sweden. So Sweden has it now.
So you left academia and went to Idaho National Labs.
That's right. I went there in 1989 and 2006.
Were you working on nuclear fusion while you were at Idaho?
Part of the time, yes. I was in the fusion safety group. It was a small group of about 6 people that looked at fusion reactor designs and safety aspects and environmental aspects. I was also involved with Center for Nuclear Engineering and Technology, with Accelerator for Cancer Research and for Space Nuclear Power and for a few other things.
Obviously, a national lab is very different.
Yes. The plus side is that there's good connection with the government and excellent staff. On the minus side was that you keep track of every hour during the week on a timesheet. At one time, I had over 10 charge number projects.
Advantages and disadvantages to working in a national lab. And
they generally have splendid laboratory equipment and computer facilities and skilled technicians to help you. They have close ties to government, so there's a lot of money flowing to the national labs. National national labs can have consortium and cooperation with universities and industry. So it's a good place to be for a research career. On the negative side, there's always anxiety about getting government contracts.
I think it might have been during that period you went and worked for the IAEA.
I worked at the IAEA full-time from 1995 to 2001 on a leave of absence from the Idaho National Laboratory. Yeah, I was head of the physics section. We dealt with research reactors, low-energy accelerators, nuclear instrumentation, and nuclear fusion research. Organized technical meetings, coordinated research projects, documents, and provided assistance to developing countries.
Where were you working?
I was working in Vienna at the IAEA Headquarters. It's a beautiful modern skyscraper there with about 2,000 people working for the IAEA. And they have nuclear non-proliferation, nuclear energy, nuclear safety, a technical cooperation department that provides aid to developing countries, and technology development department. So it's a broad scope institution, and it's one member of the United Nations family of agencies.
Were there strengths and weaknesses of that organization?
It's the world's #1 organization for coordinating all forms of nuclear activity to safeguard so that countries don't get nuclear weapons, and providing nuclear safety guidance to nuclear reactors. And it's a wonderful place to work because you have people from 80 countries getting along pretty harmoniously. So it's stimulating intellectually. They have great facilities.
After that, went back to...
From 2001 to 2006, while I was at Idaho, I was also a part-time consultant at the IAEA, so I'd go over there for a few months at a time, consulting in nuclear safety. So a lot of countries in Southeast Asia want to develop things like a nuclear regulatory commission to oversee development of nuclear power. I helped with that. In 2006, I went to the University of Illinois, where I started teaching in 2007.
You're consulting and helping with Thorium Startups right now, is that correct?
That's right. I'm doing both. I'm consulting in fusion research, and I'm organizing a new book on molten salt reactors and thorium energy. About 30 authors from various countries writing the chapters of that book. So I'm organizing it and editing it. And that will be published by Elsevier Press.
You've transitioned from fusion to thorium. Is that because fission is more near term?
Well, right now, the alternative concepts funding is very meager for concepts like stellarators. One was under construction in Princeton, and Congress cut off the money. Magnetic mirrors, they built one in Livermore in the 1980s, and then Congress cut off the money. It was never operated. There's other alternative concepts that have been defunded or never funded at all. So there's a lot of good concepts out there to be tested, but they're not getting money. That's one reason why I'm spending more time in fission research. Another reason is that molten salt reactors can operate at low pressure and high temperature without water in the core. That avoids the causes of the Chernobyl and Fukushima accidents.
Molten salt reactors are also smaller?
They can be small, yes.
What are the barriers to getting those up and running?
Done for a modest amount of money on a nuclear scale and can be done in several years. But in the United States, licensing takes 10 or 15 years for a new concept because there's no experience at the Nuclear Regulatory Commission with molten salt reactors. The United States had a molten salt reactor at Oak Ridge in the 1960s. I think China's taking the lead on this. They're building a molten salt reactor with molten salt coolant and solid fuel in the next few years, and then beyond that, they're going to have a molten salt reactor with liquid molten salt fuel, which is the thing of the future. China has 400 people working on molten salt reactors. The U.S. is going slowly, and China will take the lead in this, and then we'll be buying technology from China. Molten salt reactors can provide a lot of dispatchable energy. You can turn it on whenever you need it. You don't have to rely on the wind blowing or the sun shining.
Have you felt sort of a pickup in interest and enthusiasm in the technology?
Yes, the Department of Energy has recently become interested to the extent of having a meeting on it and encouraging companies to work on it.
Were there any startup companies that you would promote? Say I was an investor. Where should I put my money?
There are about 8 or 10 startup companies and some with big company backing. There are several companies that I think are worth investing in. I would not state their names here. In the book that we're working on, there are about 10 chapters on various reactor concepts.
Do you have any timeline on when it might be finished?
Probably early next year.
You have seen public interest rise and fall. Do you have any advice on how to deal with that?
Yes, I think there's several things that we need to do. One is to train journalists to understand nuclear technology and avoid sensationalism. Sometimes the dangers are exaggerated and the public becomes fearful of nuclear energy and of radiation. Journalism is a key profession to educate the people properly. Another thing is to teach nuclear energy in elementary education. Should know the advantage of nuclear energy and understand the risks associated with radiation in comparison with other risks in society. Another thing is that civic clubs should be encouraged to have speakers about nuclear energy. So I think if we get these three fronts, journalism, elementary education, and civic groups, that the situation will improve.
Can you say with any certainty when you think we might have commercially viable fusion energy?
I think we'll have a successful demonstration at the ITER project after 2030. So I'm confident that the technology can be developed. The economics I'm less optimistic about because I think that big machines like ITER are not going to be economical. They won't compete with fission power plants. And what we need for fusion to be commercially successful is either compact fusion reactors, such as high-field tokamaks or spheromaks, or a tax on carbon.
Money is a huge component, and if we get the technology, the money piece is still a long way off.
Yes.
Do you think that climate change affecting civilization, do you think that that will create a reason for us to invest in this kind of technology?
And people are gradually becoming aware of the climate consequences when they see lakes drying up and ice melting. And
you worked on a lot of different fusion reactor concepts. Do you have a favorite one?
Yes, I have more than one favorite, because for a large steady-state fusion power plant, I would favor stellarators, especially a modular stellarator like the Wendelstein 7X in Germany. For medium kind, I would favor a high-field tokamak like the ARC design of MIT. And for a small compact device without toroidal field coils, I would favor a sustained spheromak experiment, such as the Dynamak concept of the University of Washington.
What would the U.S. need to do to encourage the growth of those reactors?
First, it requires people in Congress to understand the benefits of fusion research and what needs to be done financially to support it. And I don't see that happening. We've got a lot of expertise out there that's just waiting for funding. And so laboratories and universities that are ready to take the ball and carry it to develop these alternative concepts.
What were the best years of the U.S. fusion program, and what were the worst?
Remember, there's the Magnetic Fusion Energy Act of 1980, but then in the following years that was not followed up. Back in the 1980s, there was kind of a purge of alternative concepts. Things like the Elmo Bumpy Torus and small stellarators and field reverse configurations and spheromaks. A lot of those were phased out.
Is there anything else that you would like to add?
We need more engineers and scientists in government. Congress, there's only a couple that are engineers or scientists. We need to give standardized tests to candidates for political office on fields of economics, healthcare, and technology. People who are voting at least know who's well educated. The president should tell Americans to thank your teachers because teachers do not get the respect that they deserve. This would elevate the teaching profession, make more young people want to become teachers, and make society better.
That's everything that I had. Is there anything else that you can think of?
Just want to express my appreciation for the opportunity to vent my emotion.
Okay, appreciate your time.
Thanks, Matt.
It was a great honor. Thank you very much.
Well, let's talk again sometime.
Okay, sure. See you later.